Okay, there we go. Okay, so hi everyone. Well, thanks a lot for having me again. I think I was there. When was I there? I think last year, no, 2019 in April, I think. Anyway, I'm an assistant professor at the School of Computing Science, Simon Fraser University here in Burnaby, BC. I direct the SFU Multi-Agent Robotics Lab, and I'm also part of the Visual Computing and Robotics group. So I really love multidisciplinary research. Right now I'm in CS, but actually in my education, I've never even studied CS, which is kind of funny. So I did my undergrad at UBC doing engineering physics and math, and then PhD in mostly EE, a little bit of CS at UC Berkeley, and then I was in the Aeronautics and Astronautics Department at Stanford. My work is in the intersection of analytical methods such as optimal control, optimization, and safety verification, and also data-driven methods like reinforcement learning, computer vision, and visual navigation. So I try to find connections between these two areas to see whether we can improve one or both of these areas using the other. So today we're going to be talking about three main topics. I'll start with safety verification, and then I'll talk about some connections between reinforcement learning and control. And lastly, machine learning, so both RL and computer vision and planning. So we can start with the robotic safety verification. And so robotic safety verification, the challenges here are mainly in the computational complexity. And as I go through this a little bit, I think we'll see why. So I'll just give one version of this. So this is called HJ or Hamilton-Jacobi reachability analysis. I won't go too deep, but we begin with some ordinary differential equations. So this is just by convention. There's also discrete time versions of this as well. So we're giving some system dynamics. So this is a model of how a robot moves. So we have the state, control, or action, as is known, better known in reinforcement learning, as well as disturbances. So disturbance just means anything that affects your system, but you do not get to control. This could be wind, or maybe it could be the action of some other agent. We also begin by defining a target set. In this case, this is a set of states that we do not want to be in. And through some magic for now, we solve the Hamilton-Jacobi equation to obtain the reachable set. And this is a set of states that will lead to danger under the worst case assumptions. So this is kind of the set that you want to avoid. So in this picture, suppose we have this danger zone as a circle here. And let's say that you're riding a bike towards this obstacle, then what you really need to avoid is the reachable set, because once you get inside the reachable set, collision with the obstacle cannot be avoided. So we kind of need to look ahead a little bit while taking the system dynamics into account. So getting a little deeper, I guess I forgot if I mentioned this, but if you have any questions, please feel free to stop me. Okay, so how do we do this mathematically? So we actually have an implicit representation of these sets. So we define some function L. This can be anything you want. So for a circle, it could be something like the distance to the center minus some radius. That could be your function L. And then we take all of these things on the left as input into this Hamilton-Jacobi equation, which is solved using dynamic programming on a grid. And then we eventually obtain this value function, V. The negative region of V tells you where the reachable set is. So again, another implicit representation. So just to dig a little deeper, I think this is something that is very familiar to me in safety verification, but I don't see it in other places so much. So this value function is defined as follows. So we start at the end here with the cost function. The cost function says, look at the minimum over time of your L function. So this basically tells us what is the worst L that your system ever gets to. That's our cost function. And then our control U is trying to maximize this cost. Well, I guess the cost is the wording cost could be unintuitive at this point. So maybe a reward here. So you control maximizes, disturbance minimizes, and then that gives us our value function. And skipping many steps, using dynamic programming, we can derive this what's called the Hamilton-Jacobi partial differential equation. And if you solve this equation, which can be done on a grid using finite difference, you would be able to get your V, your value function, and then you would be able to get your reachable set. So that's sort of the basic, the very high level idea here. Okay, so I'll just show you what we can do when we know all the information available to us, right? So let's say we know our model, our dynamics, and we know our environment, right? So we can do something like this. So in this example, we have kind of quadrotors flying in free space. We have a student a while ago controlling this quadrotor down here. Is going to fly up to try to cause a collision with these autonomous quadrotors. And you can see that once this bottom quadrotor gets close enough, the other quadrotor automatically avoids. And the notion of close enough is now kind of quantified by the idea of the reachable set. And it's also defined in the state space rather than just in the position space. So the main problem with this approach, as you can probably already imagine, we're doing everything on a grid. So computational complexity is exponential. So traditionally, I think even until I would say 2 years ago, this is what the computation time looks like. So 1 and 2 dimensional systems, not really a problem. Once you get to 3-dimensional problem, you're looking at minutes, and 4-dimensional problems, hours. While you can do these computations, you would not be able to do them in real time. So that if your environment changes or if anything changes, you would have to redo your computation, and that takes a long time. 5D and 6D, I mean 5D, I would say if you wait a week, you can do it, and 6D basically no. So this is one of the things that we looked at. So we still want to stay within the dynamic programming approach because it gives us these theoretical guarantees. We know that we're getting globally optimal solutions, but can we actually make the computation more efficient by optimizing things in hardware and software? And this is kind of like somewhat copying the deep learning approaches, right? In deep learning, we do need a lot of computational resources, and we cannot do a lot of what we do without it. So, well, for us, things are actually a little easier than deep learning. Grid-based dynamic programming is basically a bunch of nested for loops, and then you go through every grid point and you do some update. Those of you familiar with value iteration know exactly what I'm talking about. This is actually exactly the same. So very, very simple algorithm, but very expensive because of the number of grid points. So then can we somehow alleviate these challenges using optimization in software and hardware? So maybe things like looking at how the CPU works, optimizing for that, or maybe even designing FPGAs where we have complete control of how the computation is performed. And this will allow us to analyze higher dimensional systems, which I think will be useful on top of just having a globally optimal low dimension, like relatively low dimensional solution, right? Even 60 or 70 is pretty low dimensional, but I think these solutions could still be useful, as we'll see later on, to warm start some of the more complex problems. For even smaller problems, it would enable us to operate in real time. So now if you can continuously compute these solutions in real time, then we can deal with changes in the environment. Okay, so how do we do this? Maybe a very, very, actually, maybe I should pause here for any questions before I move on.
I have a question, but I see Martin asked a question first in the chat.
Okay, I'm not sure how I can look at the chat, but oh, here it is. Okay. So the question is reachable set. The solution is usually distance function is then the reachable set of contour. Yeah, I think that's a very good question. And so if I go back here, so we have Z, the state, and then our target set, as well as the reachable set are functions of the state. So the solution is really like a surface in high dimensional space. So for example, this reachable set in blue here looks like this because because the bike is facing towards the right. But if the bike is facing some other direction, maybe moving with a different speed, for example, then the slice of this high-dimensional reachable set would have a different contour. So hopefully that answers the question.
Maybe Martin will chime in if it didn't. My question was, so it looks like you're going to go towards the software or hardware side for efficiency. I can also imagine that there's an active literature doing approximate dynamic programming.
Right.
But so why not, are there limitations in the approximate case, or have people done a lot of work and realized that there's only so much you can do?
Right. So I would say these are kind of mutually exclusive directions. I actually work on that as well. I just not presenting it here, but I can talk about some challenges there. So I think if you're doing approximate DP and you just want a pretty good solution and you don't care about guarantees, I think there are many methods for doing that, even up to pretty high dimensions. If you want to maintain guarantees, then typically people want to obtain either over approximations or under approximations, depending on the application. And doing that is challenging. There are definitely several methods out there that do that. And I think the common theme here is that the higher dimension you go, the worse the approximations are, just because like if you're missing a corner in 10D, then you're missing a lot of volume. But definitely I think both approaches are valid. And I think if we can push the globally optimal solution up to a slightly higher dimension, number of dimensions, then that would also help with these other methods, which then can build on top of these slightly higher dimensional good solutions. Okay.
I had a bit of a follow-up. So you mentioned, I guess first you mentioned how you go about formulating the reachability problem as Hamilton-Jacobi. And then, like you said, in that we get a high dimensional solution. And then we extract the reachable set from that as a contour. The usual way that's done, I guess, when you actually solve the equation at the very bottom here is, you mentioned discrete methods. You would have a finite spatial grid and then iterate over time. When I've seen that formulated in the books about level set methods, generally we define a distance function formally as being the Euclidean, being the distance literally to the target contour we want to find. But then you equated the distance function with a value function. So I was curious how that means that it's not necessarily a distance the way it's defined by many books on the topics, or it.
Yeah. So this is just one convention. You can definitely choose this L function to be the distance function. We typically choose it to be the sign distance function.
That's what I meant. A sign
distance. And then if you do that, then the interpretation of the value function would be the minimum distance that you get to within the over time. So that's what that would mean.
Okay, so I see. So you don't look to redefine distance as some other value, because
you could
includes things like energy expended to get there. That could be more complicated.
Yeah, that's a really interesting question as well. If you combine multiple sort of objectives together, then you start to lose the guarantees, because you don't, like, if something becomes negative, let's say, you don't know what is causing the value to be low. It could be too much energy spent, or it could actually be a collision. So that's something that, it's an interesting question that I haven't really looked at very much.
Practically, do you know if there is something in the numerical solution that would require you to use a distance function as opposed to a function that could capture other relationships, a more general loss or value?
The theory doesn't really care what L you use. I think there's some conditions on Lipschitz continuity, but that's about it. You can, in theory, you can use anything, and then depending on what you choose L to be, you would have to interpret V in a different way.
Yeah. So as long as we can get a target contour, we could have any smooth function represent the rest of the surface for the purpose of indicating a value, for instance, different.
Yeah.
Okay, thanks.
Okay, so I think we're way behind on time, so let me let me go through this. Okay. So I think I'm gonna maybe make this quick. So basically, we have a lot of different types of computer memory, and usually the smaller, like things like register and cache, they have low capacity, but they're very fast. And things like main memory and disk, they're very slow, but they have a lot of capacity. So the main way that we're really optimizing in software and hardware is to try to use the fastest memory available. So try to fit the data, as much data into the small parts of the memory as possible. Okay, so just a very simple example. So here I have a grid, and then we're going to be iterating over this grid. And whenever we access, let's say, the 0, memory location, automatically what happens in most CPUs is that a lot of the adjacent grid points will be loaded into the cache as well. And depending on your programming language, you might be loading in sort of the order might be along the rows first and then the columns, or it could be the other way. But let's say that memory is loaded in the rows first, then the order of your for loops becomes very important. And we found that just by iterating in the right direction, we can get a lot of speed up. Okay, so in this case, in this illustration, I'm just iterating over the rows, right? And then once you figure out which direction is the fastest, you can then parallelize this. You can say, okay, we're going to be doing the computations at 2 different places at once. If you have a large cache in a CPU, this is not really a big problem, but as we'll see a little bit later, this is actually not very memory efficient, even though we're doubling the computation speed. And that's because once you parallelize too much, you'll easily run out of the faster type of memory. Okay, so don't want to go too deep into this, just the basic idea. So we implemented these 2 ideas. We simply iterated along the right direction and also parallelize the computation. And actually, it's kind of amazing what you can do with such a simple optimization. So we used the state-of-the-art toolbox. So we tested this in Python as well as MATLAB. And with our what's called the optimized DP toolbox, we're getting something like 30 times performance increase for this 3-dimensional problem. And then on some other CPU, we're getting around 50 times. So this toolbox is actually available online if you're interested in solving PDEs, or we also have value iteration implemented in there as well. So you're free to try it out. Okay, so then we wanted to see how many dimensions we can go up to. So we tried a 6-dimensional problem. The results for us is maybe not so important. This is like a specific application in underwater vehicles. So here we're basically able to do 6-dimensional problems within a few hours. So every dynamic programming time step, meaning iteration over the entire grid, took us around 5.1 seconds. And then we tried another 6-dimensional example, a humanoid robot. This time I think it just finished in 1 hour, the entire computation, with 2 seconds per step for the dynamic programming. Okay, so just going through these very quickly because they're very application specific. We also tried our optimization with tabular Q-learning. So we benchmarked this on a 3-dimensional system. So here I think somehow for value iteration, we're getting a lot more speed up than solving the PDE. So here we're getting something like 200 to even 1600 times. We're not really sure why right now. I think it must have something to do with the in-place updates of all of the grid. Whereas for solving the PDE, we have to keep track of both state and time. And that could be the reason, but we need to look into this a little more. But the point is that we can now actually do tabular Q-learning for some pretty large problems, at least larger than before. So you could have something like 6-dimensional state, 6-dimensional action space, for example. Okay, so we're going to talk a little bit about why this might be useful a little later. Okay, so next I want to address the problem of efficient memory usage despite parallelization. So here's one example of what a value iteration or maybe a dynamic programming step update might look like. So let's say you want to update this, this node here, this grid point. You will need access to some other neighbors, let's say these 4 neighbors, in order to update this grid point. So what happens in memory is that you're going to be loading in everything from this element and then across the rows all the way up to this element. And if you try to parallelize this, then in the CPU, it will look something like this. You would have to, with three parallel threads, you will need to triple the memory usage. So everything we talked about so far was basically learning how a CPU works and then trying to adapt our software to how a CPU works. Right now, what we're going to move on to is, well, what if we can design the way memory is being accessed? And we can do that using an FPGA. So in this case, we can actually have these parallel threads work on updating successive grid points like this. So then we can kind of really parallelize our computation without using much more memory. Again, just glossing over a lot of details, but so we tried this on the FPGA, and we kind of had the FPGA stream control inputs to this model card we have. The goal here is to basically show that we can use reachability analysis to guarantee safety in a dynamic environment. So in this environment, we have a student driving this car, and the student is actually trying to make this car collide with the cones. Normally, whenever the cones configuration changes, we will have to redo the computation, and that might take a few minutes to an hour. But with the FPGA optimization, we can see that the computation is just doing a 4-dimensional computation in real time. So I think it took us 0.2 seconds to solve the 4-dimensional dynamic programming problem. And then as the cones drop down and the car is able to just avoid all of these new obstacles. It was a challenging experiment to run. Okay. So I think I'll pause here briefly again before I move on to reinforcement learning and control. Okay, thanks. Yeah, I see the question by Martin again. So question is about, do we implement a numerical solution to this? Yes, so we use finite difference. And in the case of if you want the technical method, is called the Lax-Friedrichs method. I think you're probably familiar with that as well. So we use the Lax-Friedrichs approximation to the Hamilton-Jacobi equation. Let me type it here. I think it's a very common one. Okay. Yeah, so here we're looking at guiding model-free reinforcement learning. So this is something that we recently started, and there are a lot of things that we're not really sure about. So, but the idea here is that we want to solve a simplified version of the problem using optimal control. I put optimal control here, but it could also be something like the tabular Q learning. And then we use the lower dimensional solution to warm start the higher dimensional problem. So that's the basic idea. And we want to make it compatible and modular with respect to the RL algorithm that we use for solving the higher dimensional problem. Okay, so the first thing we tried was value initialization, maybe more appropriately called baseline initialization. So here we considered a simplified version of the problem. So this could either be in the form of so we convert the high dimensional MDP in RL into a low dimensional either discrete time system, a smaller MDP, or maybe a lower dimensional ODE. So whatever we happen to use to obtain the lower dimensional problem. So we can obtain a solution, for example, using dynamic programming, and then we will be able to get some value function. We also tried using model predictive control to obtain many different trajectories. And then these trajectories can then be used to obtain a value function as well. So you would just basically this is basically like a Monte Carlo. You can use Monte Carlo estimates, for example, to convert these trajectories into a value function. Okay, so now we actually do something like actor-critic learning, for example. We can use the value function to as the initial value, which is not completely correct theoretically, but if you want to be a little bit more correct, we can use this value from the lower dimensional problem as the baseline. And the idea here is that in RL, we basically have a lot of different episodes where the robot is running around trying different things, and then we want to update the policy according to how much reward is being collected. And the baseline basically says, it basically tells the algorithm what reward is considered good or bad, because rewards by themselves are kind of arbitrary. Okay, so maybe I'll jump straight into some results, and then later on I'm going to talk about maybe some discussion. Okay, so here we have a pretty cluttered environment with some obstacles. We have a robot trying to get from here to here. The input is LiDAR, two-dimensional LiDAR input, and then the output is the action. So just go straight, turn left, turn right. So a very, very simple example that we looked at in Gazebo. So first we used just PPO directly, and it didn't really learn very much. I think if you tune the reward function, there are definitely tricks you can do to make pure PPO work. But we didn't really do any of those. Then we use a baseline obtained from dynamic programming, as well as a baseline function obtained from auto predictive control. And then for all four cases, so we have two versions of each. For all four cases, we seem to be able to learn better than purely using PPO. So one thing that I will talk about is the red and the purple lines. So in the red line, we basically use the baseline that we obtained from the lower dimensional problem, and we kept it fixed. So we, as we know, MPC doesn't really give us the globally optimal solution. So by fixing this baseline, we actually limit ourselves in terms of performance, because the baseline we use is not an optimal value function. So then I think our performance got stuck somewhere around here. The purple line is also using the MPC baseline, but at a fixed number of iterations, I think somewhere around the middle, we allow the learning algorithm to also update the value function. So that includes the baseline. So then we were actually able to continue improving the performance beyond what we could do with a fixed baseline. With the dynamic programming, it was also fixed, and also, so the two lines, orange and green, they were also for a fixed baseline as well as in a baseline that gets updated. For this one, they basically look the same, and I think it's because dynamic programming gives us a very, very good solution, at least for the lower dimensional problem. So here's another kind of basically a very similar example, but this time with a quadrotor flying through some cluttered environment. You basically see a very similar behavior. PPO, I think eventually, if we let it run for longer, it might be able to learn to reach the goals, but we kind of just stopped it. We stopped it once our methods were able to reach the goal. The observations here are basically the same. For MPC, the red line is fixing the baseline and never updating. And the purple line is, I think, updating. I think we started updating pretty early on, and it really gave us a much better performance here. I should talk about what the lower dimensional problem is. So the lower dimensional problem is basically using a simplified model of the quadrotor in the car. So I think the car we simplified down to like a three-dimensional problem with two-dimensional action space, and we use tabular Q learning. And for MPC, we also use the same model. And then for the quadrotor, we use the six-dimensional model for the quadrotor. So the lower dimensional problem, for the lower dimensional problem, our policy was basically, our policy took as input the state directly. And for the higher dimensional problem, we also had the LiDAR input for both the quadrotor and the car. So basically, we're going from taking state as input to taking the observations as input for the higher dimensional problem. Okay, so this is the results. So when we saw this, we thought, okay, I think it kind of makes intuitive sense why having some kind of warm start might help learning. But to dig a little deeper, we constructed this kind of contrived example where we had a quadrature here. The real goal of the quadrature is to get to the upper right where it's going to get a lot of reward, but it's actually a very difficult thing to do because of these obstacles, as well as having to fly upwards. We had a trap, what we call a trap, where we give the quadrature a little bit of reward, not as much as the goal, but this is very, very easy to get to. The quadrature basically just needs to fall down towards the left, and it will be able to get a good reward. So then we tried just a pure learning-based approach, compared it with our approach. So the baseline means the baseline here means a purely learning-based approach. It's kind of a overloaded term. So here, let's just focus on the green for now. So this plot shows us how often the agent gets to the goal, and the dashed line shows how often the agent gets to the trap. So here, as we perform learning, we can see that the goal rate doesn't really improve very much, whereas the trap rate actually improves quite a bit. And that kind of tells us that if you were just doing a purely learning-based approach, the quadrature is kind of somehow incentivized to go here because it's pretty easy and you do get a better reward than crashing anywhere else. If you actually try to get to the goal, there's a very high chance of hitting any one of these obstacles, or maybe just flying off to somewhere else. So that was the two green lines. For the two orange lines, what we saw was that if we initialize the baseline function using the value iteration solution, we can see that very quickly the agent learns to reach the goal a lot more often, whereas the agent initially kind of reaches the trap sometimes, but eventually it stops trying to go for the trap. So this is kind of the observation we made, and I'm gonna and then we were wondering, okay, that's pretty interesting. So let's look at the estimated policy gradient compared to the true policy gradient, and we're thinking, okay, maybe we have a better gradient in this case. And we do have a better gradient. So this plot shows the similarity between the approximate policy gradient compared to the ground truth over the number of samples we take. So the number of trajectories we take. We can see a little bit of, so the blue one is from our method and the orange one is a purely learning-based method. We saw that actually the gradient is a little bit more accurate for us. So before I continue, I do want to say that I think gradient is not the only story here when we want to learn a policy. So gradient is only important. Gradient is the only important thing whenever you have a complex problem. And when you don't have a complex problem, I think gradient is only part of the story. We're hoping that with this very simple example, gradient is probably more important compared to some other even more complex examples. So that's what we're hoping for, but we don't really know here. Okay, so we're seeing a little bit better gradient. So looking a little deeper, I'm just going to draw some arrows here to depict kind of how one would compute these, how one would approximate policy gradients in actor-critic methods. So basically, we have these arrows. Each arrow represents an episode. And then depending on how well you perform in the episode, you're going to scale these arrows with a reward, or maybe a reward, the return minus baseline. And what you're going to do is you're going to keep on doing this. And in the unlikely event that you actually found the goal, you might get a very, very high reward pointing in some other direction. And maybe this really long arrow will cancel out the effect of all of these other small arrows that point towards the trap and give us hopefully something close to the true gradient. So ideally, this is what we should be getting if we have many, many episodes. But with a limited number of episodes, what we might see is that, okay, maybe we only have these 3 arrows and we were never lucky enough to get this other really, really high reward, episode. So then the approximate gradient now is kind of pointing in the wrong way. Kind of just a rough drawing. So that's kind of the intuition. So what we're thinking with initializing the baseline function from control methods is, well, because we kind of know because we have some approximate idea of what kind of return we should be getting. In the case of the trap environment, we should be getting something like 1,000 discounted over time, right? So if you're not getting that value, it means that you're doing a bad job. So even if you reach the trap and you got something like discounted 100 reward, that's still not a good return. So all of these arrows, because after subtracting the return with the baseline, we're going to get a negative number here because the baseline tells us you should be getting something like 1,000, but you only got 100. So then this multiplicative factor in front will be negative, and it's going to flip the direction of these arrows, right? This is I don't really know what actually happens with the gradient, but this is kind of like what we're thinking might be happening. So at least in this particular contrived example, we can see that perhaps we're getting better gradients because so basically the baseline from the approximate solution is helping us get a better gradient. Okay, so I'm going to pause here a little bit.
Martin has a question in the chat, and then I want to ask one.
Okay, so is initialization same as running a simulation or initializing with some heuristics? Yeah, so here we're initializing with some heuristic. More specifically, we simplified a problem down to a problem that we can solve using, for example, tabular methods like Q-learning, or maybe a problem we can solve using MPC. And then from either MPC or something like dynamic programming, we can get the approximate value function.
Is it so that the kind of key problem you have is a fixed spatial discretization, and then the time it takes for the method to update that discretization? So what I was wondering is the heuristic essentially a coarser spatial discretization, or is it something completely different?
Yeah, something completely different, you could say. So the original problem is a high-dimensional problem that you will not be able to solve just by discretizing the state space. So for the high-dimensional problem, we'll be doing trial and errors, kind of just standard reinforcement learning. So using that to solve the problem. For the lower dimensional problem, we're actually solving the problem in a lower dimensional state space. So if the original problem is, say, 20 dimensional, we simplify the problem into like a 4 or 5 dimensional problem, so that we can solve it using discretization of the state space.
So can I think of this as the same as transfer learning, where you have a source task that's simpler and then you solve it and apply it to the harder task?
Yeah, I think it's similar to transfer learning, except that the task is the same, but the representation of the task is different.
And then I liked your argument for why this will help you not fall into the trap and actually go to the goal. But if you used optimistic value initialization, then you would also know that the trap was a trap, it was not the true goal. Or you could maybe use a potential-based shaping reward that just gives you the distance between that and the goal. So those methods, I think, will be a lot simpler. So I think I'm missing why you want to use your actually pretty cool method where you use the smaller dimension.
Yeah. So I think in the very simple contrived example, that was kind of for us to understand what's really happening, right, with the estimate of the gradient. For some other problems, you may not have a good heuristic for the problems. So, that's kind of what we're targeting. So when you do not have a good simple heuristic, what we then need to do is to use these control methods or maybe dynamic programming to actually solve the problem in a more nuanced way, at least the approximate problem. Yeah,
Okay.
yeah. So we're kind of looking at situations where the dynamics of the system is somewhat complex, like the quadrature, for example. It may not be so simple. Like the distance, I would say, is definitely not a good heuristic. Yeah, so that's kind of what I would say. But we haven't compared with optimistic value initialization. I think it's something that we should probably do.
So you're looking for a place where you don't have a simple heuristic that you can just write down, but you do have a way of designing or picking a good low dimensional abstraction.
Yeah, yeah.
Okay, cool. Thank you.
Yeah, no problem.
As one other follow-up question, just to continue with what Matt said about optimistic value initialization, I can see how this is better because you're sort of telling the agent, here's what you could achieve, and it needs to figure out how to achieve it. Whereas optimistic initialization could wash out too quickly, and that's hard to control. But I guess one question I had was, you learn a baseline in this more abstract space, and then you use it within the policy gradient method, I think is what you're saying.
Yeah.
Well, how is that mapping done? Like when I query my baseline learned in the other space, how am I using in the true space?
Yeah. So in many situations, it's pretty easy to design. So for example, with the car, you can simply omit. So we tried a few things. One is when we have these additional states in a high dimensional space, we even try just putting random numbers or all zeros. And that seems to work. A better way of doing it is for example, for the LiDAR, whenever you're doing anything with LiDAR, you can compute maybe with some noise what each LiDAR reading should be. So that's something you could do as well. We haven't really formalized a general way of doing this. So, but I think but that could be done using some sort of encoder, for example. Maybe you might be able to learn a mapping to go from the high dimensional space to low dimensional space. So that's something that we haven't really looked at yet.
Okay, thanks. Yeah, nice.
Okay, so I think it looks like we're almost out of time. I'm happy to share my slides, but I'm going to kind of skip this next one and go directly to machine learning plus planning. Okay. Okay, so here we're looking at this problem of following ahead. So the idea is, let's say you have a guide dog, or maybe I like to think of the shopping cart. Let's say you're shopping and then you're just walking around, and right now we have to push the shopping cart in front of us. But what if you could have a shopping cart that is just in front of you autonomously, and no matter what you did, right? You're just walking naturally, and can we get something like a shopping cart or maybe a suitcase to stay in front of you? Okay, so here we took a hybrid approach which combines RL and planning. So the reinforcement learning part is we just implemented D4PG, which is it's like a Q, kind of similar to Q learning, I guess. But the difference is instead of outputting a short navigational goal, instead of outputting the actions directly, we actually output a short navigational goal. So this is kind of illustrated on the right here with the robot. The output of the policy network is going to be some goal nearby. And the goal is parameterized by, I think, we tried position as well as position and heading. But in general, you can parameterize the goal whatever way you want. We also use curriculum learning to kind of to improve the data efficiency, but nothing so new here in the RL part, except that we're outputting a navigational goal. To get to this goal, we use a classical trajectory planner. And the idea here is that we don't really need to learn what we already know, right? We have so many different planners, so we should use them to get to these sub goals. And the reinforcement learning can then worry about this higher level task of choosing where to move to next. Okay, and we found that by doing this, we're actually able to achieve zero-shot synchronous transfer, whereas if we simply output the action of the robot directly with the policy network, we're not able to do that. We call this the end-to-end method. Let's see. Okay, so we compared the performance on this task with 3 different methods. LBGP is our method. HC is a previous purely classical method, and then E2E, end-to-N is outputting only the actions, directly outputting the actions instead of having a goal. I will say that end-to-N actually worked the best in simulation. So we started working on this with an end-to-N method, and it was working really well, but we weren't really sure whether it would translate to the real world. And it actually turns out that in many situations, it doesn't. Later on, when we just made a simple change of outputting a nearby navigational goal instead of the actions directly, and then getting to the goal using a planning method. And that actually works really well, just without any additional training in real world. So that was quite interesting to us. So we did several different experiments. In all of these experiments, at least in this set of experiments, we have the person moving in an S shape, and we had the robot starting in a few different places, like front right, front left, and behind. So in all cases, we had the best performance. So here I have all of these cases playing. So this is done in the motion capture room. So the input to the policy is actually the relative state, the relative position and orientation between the person and the robot. So maybe I think if we focus on the left top one right now, you can kind of see somehow the robot is implicitly predicting what the person might do. So as soon as the person turns a little bit, the robot kind of knows to go the other way. And a challenging scenario is actually bottom right, where the robot actually starts behind the person. So you can kind of see that the robot took a shortcut here once it realizes the person is going this way. Okay, so the baseline method using the purely classical method, which also tries to predict where the person is going, but you can kind of see that the robot kind of reacts a little too slowly. It doesn't really pick up on some of the more nuanced movements of the person. Okay. So I'll just play that again. In the end-to-end method, it just didn't work. The robot kind of just moved to the side for some reason, and it never looked like it was trying to follow the person. Sorry, okay. Some other examples we did, person walking in a U shape. Again, with the robot starting at a few different initial places. So you can kind of just get an idea of how the robot appears to predict where the person is going, even though we don't explicitly do any kind of prediction. So maybe I should talk a little bit about how we train the robot in simulations. So in simulation, we basically randomize a lot of different paths. So we hand chose a few different paths. So we had the person moving in a straight line, in an S shape, in a U shape, in circles of different radius at different speeds. So we basically handpicked a few different types of motion and then randomized the parameters of those types of motion. And then the curriculum learning part is that we start with a straight line, which is pretty easy to learn. And then we kind of hand design the order of which kind of trajectory of the human is more difficult. So basically train the policy like that. The reward function was basically, if you're in front of the robot at around a 2-meter distance and within, I think, 45 degrees, in front of the robot, then you continuously get a high reward, and everywhere else you get a very low reward. So that was the learning setup. Okay, again, just the baseline method, which is a classical method. You can kind of see the robot just goes too far because it doesn't really realize that the person is going to come back. Okay, so that was, I think the point of that was, well, first of all, kind of an interesting real world application, I hope. And second of all, just changing a little bit of what the policy network should be doing, right? Instead of outputting the action, we should maybe output a nearby navigational goal. We also tried the same idea in visual navigation. So here I'm going to skip. So due to time constraints, I'm going to skip a little bit. So the end-to-end method would be to go from pixels to actions. But here we'll take the approach of going from pixels to waypoints or nearby navigational goals. And then we use a trajectory planner to get to these waypoints. Same idea, no need to learn what we already know. Okay, so we train in simulation using actually supervised imitation learning. In this case, we use the Stanford indoor data set, and then the results are actually transferable to real life without any additional learning. So I'll say a little bit more of how we generated the training data. So the training data was generated using optimal control. So let me just pull up. Sorry, let me skip this slide and just show you the two things we tried. So the first thing we tried was to use the distance heuristic, where we tell the robot to stay a little bit away from the obstacles while you try to get to the goal in simulation. In simulation, we have complete knowledge of the environment, so we are always able to generate the optimal waypoints to get to the goal. And then the data we collect would basically be rendering a scene like this, and then that will be the input, and then the output would be what is the next waypoint that the robot should move to. So what we found was that using the distance heuristic, a lot of times if we used too much buffer zone between the robot and the obstacles, then the training data was really bad because the robot in simulation was actually not able to go through this buffer zone to the goal. But when we decrease the buffer zone so that the training data actually allows the robot to get to the goal, due to the imperfection of training, of imitation learning, the robot actually tends to collide with the walls a lot. So we were actually not really able to find a balance between reducing the buffer zone and to get good training data versus kind of having too much error during test time. So then we took a optimal control inspired approach where we first compute the time to reach the goal. In the time to reach the goal, so this function was defined on the position of the robot, the speed of a robot, as well as the orientation of the robot. So the idea here is that we should be defining the quality of a waypoint not only based on the position, but also based on the orientation and speed and the dynamics of the robot. And instead of creating this kind of buffer around the obstacle, we actually said, let's add some disturbance into the system. And the disturbance is basically kind of trying to preempt the fact that imitation learning is not perfect. So if the training data contains trajectories that are successful despite unforeseen disturbances, that means that during test time, despite some errors in the policy network, in the imitation learning, the robot could still be able to pick good waypoints. So that's kind of, so this is the approach that we used. Okay, so then we tried this in a real world as well. So with our method in red, we're successfully able to go through some narrow doorways at SFU. With some of these other methods, especially the end-to-end methods, they actually worked reasonably well again in simulation, but they could not transfer to the real world without any additional training. So here's a third-person and first-person view. So this is kind of like a doorway that we had the TurtleBot 2 go through. I guess it's not very, very fancy, but I guess the main point here is that we're investigating predicting waypoints instead of the action. And this whole thing was done using just a single monocular camera. Analyzing the failure cases and success cases again a little further, we found that, so here we have in blue our method, and in orange the method that used the buffer, like some distance buffer as the training data to generate the training data. We found that the two methods are actually comparable with medium and easy tasks where the openings of the corridors and doorways are pretty big, and where we're getting most of the benefits using our method was when we had to get through very, very narrow places. So here we have much better success rate. The overall success rate is actually not, I mean, nothing to, nothing to be proud of, but I think a lot of the failures were due to the robot lacking memory, right? We're simply looking at a single image and then trying to predict the waypoint. So a lot of times the robot will kind of forget what it has seen before, and that led to a lot of failure cases. Okay, I think that's all. So thanks a lot, everyone, for attending, and I'll take any questions.
So I was wondering, it seemed to me you used fixed spatial coordinates. So that was my guess anyway, that you would have like your discretized space in a 2D map as is common. Often as a problem becomes easier or harder, that can depend on how we formulate the reward function, but it could also depend on how we formulate the task. So what do you think about that? For instance, we could center the coordinate system in the agent, or we could center the coordinate system in the case of the leader task, the shopping cart, virtual shopping cart. What if we had centered the coordinate system on the leader?
Yeah. So we tried that. I actually don't remember which one worked better, but one of them worked better, and we weren't really sure why. Yeah, sorry, I don't quite remember this part, but we tried both. In the end, we stuck with just a relative. Yeah, so we centered it around the robot, I think, in the end, just because we thought that that's a little bit more realistic, because the robot could measure kind of where the person is relative to the robot more directly, I guess.
Matter if those were LiDAR coordinates or visual coordinates from a Kinect or something, as long as one cuts a 2D slice out of it, but we don't necessarily have a Euclidean geometry.
So not too sure if I entirely understand.
So instead of having Euclidean coordinates, if we had something that's more related to a sensory coordinate space, non-Euclidean, for instance, the projective coordinates that we can get out of a camera, would that be a limitation?
I'm not sure, actually. Yeah, we didn't really, for the follow ahead experiments, we actually just went to the Vicon room, put some markers on the person and the robot, and we calculated the person's relative orientation and position. So we didn't really consider what you're saying.
Okay, thanks.
I have a question on the visual navigation example.
Okay.
So you mentioned I guess the action space are the waypoints. Is that?
Yeah. So I think the action space is the waypoint. So I think in this case we had position. So the relative position and orientation of the waypoint.
Is there any constraint in the like a waypoint? Say it's not too far from the robot current position, or?
There's no constraint actually, but the training data would not have anything that is infeasible, because we generated these waypoints by using trajectory planning methods in simulation.
I see.
Yeah. So it turns out that during test time, we never had a case where the waypoint was way off somewhere really far away.
And a related question would be how robust is the trajectory planner, like the classical ones you tried? Is it like super reliable, like you never had to worry about it, or you had to like pay more attention in that?
So the classical planner we used was actually the globally optimal plan. So we used dynamic programming to basically plan a trajectory to the goal. while taking into, so the tuning parameters were basically how much disturbance do we expect? So how much noise in the state as well as in the input we had. So we put all of that into like an optimal control problem, and then we use dynamic programming to solve that problem. So the solution we get was always globally optimal.
And that's on the original environment, not like a approximation to it, right? Or
No.
like
So
a lower dimensional.
yeah, it's in the lower dimensional problem. Yeah.
Okay. Cool. Thank you.
Yeah.
Okay, if no one else has any questions, since we're a few minutes past 1 o'clock, we might end it here. I think I sent out a sign-up sheet for one-on-one meetings with Mo, and I think everybody has taken up the time slots that were available. So thanks to those of you who signed up and who joined us today. And if you have any questions about any upcoming AI seminars, you can contact myself or Neeraj, or you can have a look on our AI seminar website as well. Okay, thanks everyone for coming, and we will see you next week.
Okay, thanks everyone. See some of you in the afternoon.
Thank you, Mo.
Thank you,
Bye.
Mo.